Hello. Okay, so today we are continuing on in the second day of our thermodynamics unit. The first thing we're going to do today is just take a quick look at this warm-up question to review the things we talked about during the last lesson. So the question says, which of the following is not true regarding temperature? Okay, so using the information that we talked about in the last video and also in the PowerPoint notes that you have access to, take a moment and see if you can answer this question. Which of the following is not true regarding temperature? Okay, so let's look at our answer choices. A says water boils at 100 degrees Celsius. If you look back in your notes, that is a true statement. Water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. That's kind of how the Celsius scale is defined, actually. In the Fahrenheit scale, which we use in this country, but the Fahrenheit scale is not the scientific unit of temperature, we use 32 degrees Fahrenheit is the freezing point of water, and 212 degrees Fahrenheit is the boiling point of water. But A is definitely true. B, at absolute 0 or 0 Kelvin, all atomic motion within an object stops. That is also a true statement. That's what is meant by absolute 0. That is the lowest possible temperature an object can have. C says temperature measures the average kinetic energy of an object's atoms or molecules. That is true. That is like the definition of temperature, and we talked about that in the last video. And D says pressure measures how fast particles of a gas are moving. That is the one that is not true, so D is the answer that you should have chosen. Pressure, in the context of this class that we talked about last class, pressure has to do with how often or how frequently the particles of a gas collide with their container walls. So D is not correct. That's the answer that you should have chosen. So this is just a summary of some of the things we talked about before. Okay, we just talked about some vocabulary terms last class. Thermal energy, heat, temperature, pressure. We also talked about thermal equilibrium and how when two objects are in thermal contact, they transfer heat between them from hot to cold. Just to show you what that looks like, by the way, I've got the simulation here. So we've got two objects. The object on the left is at 4 degrees Celsius, and the object on the right is at 40 degrees Celsius, so much hotter. And when I hit play, what we're going to see is the heat is going to transfer from right to left, and eventually, after a long enough time, they're going to reach thermal equilibrium. So here we go. Okay, you can see the spread of heat visually. And remember, in thermal equilibrium, the two objects reach the same temperature and there's no net heat flow between them. So we can see on the graph, over a long period of time, it might take a while, it might take a few minutes, but eventually their temperatures reach the same level and there's no more heat flow between them. And you can just kind of see visually they're at the same temperature and they appear to not be exchanging any heat between them. Okay. So that is what thermal equilibrium looks like. Now, going back to the notes, today we're talking about the laws of thermodynamics. The laws of thermodynamics are kind of like Newton's laws for motion. They're just like the overall key concepts that govern this unit. So thermodynamics is the study of heat, and which, as we learned in the last class, heat is the transfer of thermal energy. The laws of thermodynamics have to do with the heat and how it's transferred in different situations. And so we're only going to talk about two laws of thermodynamics, and we're going to talk about one at a time. Law number one, the first law, is basically a statement of the conservation of energy. Okay, energy cannot be created or destroyed, but it can be transformed into different forms. And we're going to write that in an equation that we've never seen before, and we can see there's an equation that goes with it. This equation right here, this is the first law of thermodynamics, and we'll talk about that on the next slide. And then the second law, there's three different ways to state the second law. And again, we'll talk about each of these in turn. Entropy of a system always tends to increase. You could also say always naturally increases. Now we'll talk about what entropy means on the next slide. Another way of saying this is that heat always tends to flow from hot to cold on its own. Or you could say that a 100% efficient machine can never be built. And so you might not know what entropy means, you might not know what efficiency means. We'll talk about all those things in time. But these are the two laws. The second one is kind of the more complicated one because there's different ways to get at the same idea. The first one is really straightforward though. Okay, so let's talk about the first law. So in the equation for the first law, notice we have three equations. We have Q, we have W, and we have delta U. Okay, so I'm just going to kind of write out what each of these represents. Okay, so Q is the symbol for heat. Okay, I don't know why we use Q for heat, but that's what we use. Okay, the unit for Q is joule. The reason is, and we've seen joule before, it's a capital J. The reason is, remember, heat is the transfer of thermal energy, and so Q should have units of energy. Okay, so going on to the next symbol, we have W. W we've seen before in a different context. Okay, W stands for work. Okay, we saw work in the last unit. Work is done whenever a force acts over a distance. And the unit for work is also the joule, and we saw that in the last unit as well. Okay, now again, work is done anytime a force is acting over a distance. And so we'll see in the context of this unit, typically work is done on a container when the container expands or contracts, when there's a force acting over a distance. For example, if you're pumping up your bike, when you press down on the bike pump, you're pushing the piston into the pump, and that's a force acting over a distance. That's an example of work being done in one of these situations. Delta U stands for internal energy, and in problems you sometimes see this as energy absorbed or released. The unit is also the joule, so everything is measured in joules in this equation. And again, here is what the equation says. Q equals W plus delta U. Now, this is the first law of thermodynamics. Okay, that's what's in the notes. Now, basically what this says, it says in the notes this is like the conservation of energy. And basically what this is saying is, let's say you add heat to something. That's our Q. If you add heat to something, okay, that means you're adding thermal energy into a system. There's two places that energy can go. Either it can go to doing work, which is our W, or it can be absorbed by the material inside the container, inside the system, in the form of internal energy. Okay, but the work done and the energy absorbed cannot be any greater than the heat that you added. Okay, so what we'll see is we'll see a few examples, but really the problems you're going to see with the first law of thermodynamics are very simple as long as you know what everything represents. Okay, so if you need to pause here and make sure that you're good on this equation, we'll do some examples. Okay, so I'm going to clear this. We'll do some examples. Example 1, it says, consider a rigid, unbreakable steel can of air. You heat the can from underneath with a Bunsen burner. What happens? Okay, so I'm just going to type this out. If you heat the can with a Bunsen burner, what would normally happen is the can would expand, but it says it's a rigid, unbreakable steel can of air, and so the can, no pun intended, cannot expand because it is an unbreakable can. Therefore, if you think in terms of the first law that we just saw, when you add heat to something, either that energy can go to doing work, or it's absorbed by what's inside the container. Now in this case, there's no work being done, because if the can cannot expand because it's unbreakable, right, it's made of some magic material that's unbreakable, if the can cannot expand, that means there's no work being done. Okay, therefore, all of the energy, all of the heat will be absorbed by the gas inside the container. Okay, now for the second question, it says, now let's suppose the top of the can is free to move. Again, you heat the can from underneath with a Bunsen burner. What happens now? Because the can now expand, again, pardon the pun, some of the heat added will go to work in expanding the can, and the rest will be absorbed by the gas inside the container. And again, what the first law says is basically conservation of energy, is that all the heat you add in, whatever doesn't go to the work expanding the can, is going to be absorbed by the gas inside the container. So it's basically like conservation of energy. Okay, so that's example 1. Now, example 1.5, it says a cylinder holds an ideal gas at room temperature. 1,000 joules of heat is added to the gas. How much heat is absorbed by the gas when it does no work on its surroundings? Okay, so pause here. I'm going to do this question over here on my whiteboard. The first question, we're told 1,000 joules of heat is added to the gas inside a container. Okay, so heat is added, so that is our Q. Q equals 1,000 joules. And I'm just going to write the first law over here, Q equals W plus delta U. Now we're also told we're also told that no work is done on its surroundings. Maybe it's made of some unbreakable material. Okay, if there's no work done on the surroundings, that means Q is 0. Okay, so if we have Q equals 0 plus delta U, and we know Q is 1,000 because that's added as heat, that means delta U, the internal energy, or in other words, the energy absorbed by the gas, is also 1,000 joules. Okay, so there is our example 1.5, at least for the first one. Okay, so this is example 1.5. Now, the second one, I'm just going to clear this for a second, so pause it here if you need to. The second one is the exact same question, except now it says 1,000 joules is added. How much heat is absorbed by the gas when it does 300 joules of work on its surroundings? So exact same question. Q is still 1,000 joules, but now it tells us that the work done on the surroundings is 300 joules. Remember, whatever is not done by work has to be absorbed by the gas. So if we have 1,000 equals 300 plus delta U, we want to know how much is absorbed by the gas. We're looking for delta U. Okay, to get delta U by itself, we have to subtract 300 on both sides. And so delta U, which is the amount of thermal energy absorbed by the gas, is going to be 700 joules. Okay, so just another simple example with the first law of thermodynamics. Okay, so pause there if you need to. Okay, so that is it for the first law of thermodynamics. In the next video, I'm going to talk about the second law of thermodynamics.